నాకు దీంట్లో కూడా వస్తలేదు ముఖ్యంగా వచ్చిందా ఇక్కడ వస్తలేదు నాకు ఇయర్ ఫోన్స్ వస్తలేదు ఉందని అప్పుడు వస్తుంది లైవ్ అది వస్తుంది కదా అది చెప్తున్నాను కదా
So FinFET technology, this FinFET technology as fin field effect transistor is a 3D non-planar transistor which is designed in terms of what? By replacing the traditional 2D transistors. So how the 2D transistors will be representing? So the 2D transistors in the normal we are having the source gate and thing, and the normal CMOS inverter. Whereas in the FinFET technology is based upon 3-dimensional transistors, it significantly increases the contact area between the gate and the channel, which reduces the energy-based stop current leakage currents and enable faster processing. So how it works? Whatever the conducting channel you are having in the source and the drain, whatever the conducting channels you are having the vertical fashion. See, so the conducting channel between the source and the drain is shaped like a vertical tube sticking up from the silicon substrate. So this gate is oxidized in the vertical fashion so that we can dope n number of source and the drain materials and they can fabricate parallel. Whereas in the case of normal 2D technology or CMOS technology, we'll be having the single source and drain, or we'll be having the NMOS or the CMOS, and we're having the gate oxidation, which are fabricating in terms of 2-dimensional. And here, whereas in the case of FinFET technology, we are having the gate is fabricated, gate is vertically, flipped or vertically fabricated, where the n number of source and drains are n number of NMOS or n number of CMOS fabricating on a single silicon substrate, and they are isolated from each other. So in the case of 3D gate, we are having, instead of gate controlling the current, okay, the gate, whatever the gate you are using, this gate wraps the entire 3D field in a three distinct sides. We are having three distinct sides in the three-dimensional gate. So this multi-sided, okay, will allow the transistor to follow the electron tightly. So without any dimensional strictness and without any leakage, we can flow the electrical current. Right? So coming to the next technology, the advanced technology we are having. Next slide, please. So gate-all-around technologies. So what is the gate-all-around transistors we are having? It is a cutting-edge semiconductor architecture where the control gate wraps entirely 360 degrees, okay, around the transistor channel. So this will replace the FinFET technologies because we can wrap the gate entirely in the 360 dimensions. So this here what you can have this while the gate uses the FinFET technologies, we have seen that in the normal planar 2D technologies, the gate only one gate controls the channels from only one side. Whereas in the FinFET, the gate or whatever will be having that will be controlling in the three sides. Whereas in the case of gate all around transistor fabrication technology, it controls or it surrounds the channels in all the four dimensions and it creates a perfect shape, okay, in order to reduce the current leakage. So all the four dimensions, because whatever the transistors you are fabricating or whatever the IC you are fabricating, okay, so because silicon, okay, what are the you are having the four dimensions, so we are having four valence electrons, okay. So in that one we have to control the all the valency forms. So those are controlled and we can control the leakage current in the gate or around transistor level design. So that is the basic functionality and which wraps the 360 degrees of transistor channel in all the dimensions. So next slide please. So here you can see we are having the planar or whatever the CMOS technology or advanced fabrication technology are having. Okay, so those are nothing but the planar technology where you are having the single source and the drain and the gate is isolated from the source and the drain. Okay, whereas in the case of FinFET technology, the gate is vertically fashioned and these are available in the 3D dimensions in the FinFET technology. Whereas in the case gate all-around technology, the gate is wrapped in all the 360 directions and in all the four dimensions we can able to see. And we can dope n number of sources and the drain and we can see and in all the 360 angles also. So these more advanced versions. So till it has to come into the market. Okay, so these are the future trends or the future technologies into the industry 5.0. So FinFET is also came into the existence, but till now it has not completely up to the market. Okay, because some leakage issues, currents are there. So those are advanced technologies we have to go with the gate or other technologies. We can have leakage currents will be reduces in all the dimensions. Next slide, please. So next one is next to technology is nothing but the come up in technology is nothing but the 3D IC integration. So what is the 3D IC integration you are having? So you're having the 2D layout you are having nowadays. Okay, whereas in the 3D IC die stacking, so vertical integration will be done. So it is a semiconductor packaging technology where multiple distinct chips or dies are they are vertically are interconnected within a single package. So vertically they are interconnected. So by moving from flat 2D to the 3D IC integration, it reduces what shorter interconnecting lengths. Yeah, yield higher bandwidth. Okay, low latency, reduces the power consumption, and a smaller physical footprint. So this 3D IC integration has it is coming into the market where you can go for the vertical fabrication, where you can go for vertical integration of all these designing and which reduces the power consumption. So instead of manufacturing a massive system on chip on a single wafer, so system on a chip consisting of what different ALU or different processors or whatever you are having multiplexes, you are fabricating on a single chip. So instead of manufacturing a system on chip on a single wafer, which we are going for what 3D IC integration where you can fabricate on different wafers also. So it breaks the system into the smaller specialized functionality chips, okay, which are called as what chiplets. So this cyclic integration will convert into the smaller or specialized functional chips called as the chiplets. So these chiplets are then stacked and electrically connected with several advanced techniques, okay, which are the upcoming technologies will be used in order to go for the IC integrations. So next coming technology is nothing but extreme ultraviolet lithographic technology, where the normal lithography technique where you can have the photolithographic material, photoresist material exposed to the ultraviolet rays to a mask, it will create only a window in the mask in order to dope the materials. Whereas in the case of extreme ultraviolet lithography technique, which is the advanced version of fabrication technology, it is a more advanced version used in manufacturing semiconductors, which uses 13.5 nanometer of wavelength light to etch the sub 10 nanometer of transistor patterns onto the silicon. So this is nothing but the extreme ultraviolet technology. So here, whatever the light sources are having are high-powered laser pipes, okay, which are done at molten tin droplets, and it creates a plasma that emits the UV light, and the vacuum chamber, whatever we will be having here, that okay, extreme ultraviolet lithography technique is absorbed by the air, so that the entire process requires a high vacuum. So since this light cannot passes through the standard glass lenses, the system uses a complex array of ultra flat mirror and shrink the light pattern onto the photoresist coated material. So as you seen here, this will enable the nanoscale precision, allow manufacturing to pack tens of billions of transistors on a single chip, okay, which are available in the finger name. So it increases the efficiency. The chips built with the EUV consume less power and delivers significantly high performance compared to the of the older methodologies. And what are the next technologies you are having? So we are having the nanometer scale fabrication technologies. So in the case of nanometer fabrication technologies, whatever you are having, combined nanometer, okay, the next technologies are upcoming is nothing but 3 nanometer or 2 nanometer technologies representing the okay edge of the semiconductor manufacturing. So moving below the 5 nanometer of technologies, like we are having shifting from the thin film to the gate or the transistors are little bit different. So it provides a massive okay steps in the transistor densities, or energy efficiency, or artificial intelligence performance. So these different technologies are involved in designing the different semiconductor technologies for fabricating or silicon. So whatever the important fabrication which whatever the chip was having, so how the chip has been fabricated, we for the oxidation, going for the PCB, you're going for the etching process, you're going for doping ion implantations, you're going for the thin film depositions using chemical vapor deposition or physical vapor deposition. Okay, then you're going for metallization, interconnections, and then you're going for what? Reaching the higher industry 5.0 synthetic technologies consisting of nanometer scale fabrication technologies, gate all-around technologies, FinFET technologies. So these are all coming up to the market. So these fabrication plays a very important role, which increases the packaging and reduces the performance and less power consumption. So, so what are the emerging trends you are having in the real? So coming to the CMOS technology, as we know this one. So we have CMOS and the PMOS fabrication, and we are having the two oxidation layers. So this already we are having coming in this market. But what are the advanced technologies related to the fabrication we have so that those are coming into the market. Next. So what are the emerging trends in the VLSI? So based upon the fabrication which are used in the Industry 5.0, so what are the emerging trends in the VLSI? We are going for the artificial intelligence, okay, which will do the dedicated hardware design and we can design for the system on a chip where multiple functions can be integrated on a single chip, and we can go for network on a chip where efficient or chip communication can be done, and we can go for 3D IC technology where vertical chip fabrication can be done, and we can go for the FinFET technology which improves the transistor performance in terms of three dimensions, and we can go for the chiplet model chip integration approach where we can go for the 360 angle of power leakage power reduction can be reduced. So these are the emerging trends that we are based upon the FinFET fabrication, are based upon chiplet, are based upon the 3D IC integrations, are based upon network on chip application, are based upon system on chip fabrication process, are based upon artificial intelligence as well as design fabrication methodologies. Next slide. So advanced semiconductor technologies in the industry 5.0, where this is the backbone for the modern electronic systems. And what are the design principles are required? It ensures variability, reliability, and efficiency. Okay, and these are very much included in order to develop your VLSI systems, starting from VLSI design hierarchy, designing the top to bottom or bottom to top approach methodology. So whichever the methodology is feasible. Okay, so whether you want to go from top to bottom methodology or bottom to top methodology. So what are the feasible techniques you have? How you are approaching the design? How you want to reduce the power consumption in order to increase the scalability of the system, in order to increase the reliability of the system, or in order to increase the efficiency of the system by adding the different design principles like modularity, regularity, or scalability to useful the design. And thus nowadays we are going for the CMOS technology, which dominates the digital IC design. But at the same time, we should have the low power or high performance design. Okay, are the major constraints and major objectives for the future technologies. So we have to design the VLSI or whatever the design fabrication we're having. Those design fabrications has to be less power consumption and which has to be for the high performance design by using FinFET or by using gate-all-around technology or by using 3D IC technology integration or by using nanometer technology. So, which reduces the low power and high performance metrics will be met. And whatever the you're having, so the advanced semiconductor technologies, future growth is driven by artificial intelligence, and the system on chip designing, where you're having different types of processes and integrating things. Not only the processor, we have the actual processor, we have different types of processor we will be fabricating. We're having the FinFET technology, we are having the chiplets, and we are having the 3D IC applications. So these are the different advanced semiconductor technologies which are driven based upon the VLSI, and without the VLSI, no future whatever enhancement has been done. Okay, no processor has been done. Without the IC, we cannot design the processor. We cannot design the upcoming AI technology. So VLS is the backbone for whatever the technologies we are fabricating onto the IC chips. Hello.
Yes, ma'am.
Hello, Ramya.
Yes, ma'am.
Yes, ma'am. I completed my presentation.
Yes, ma'am.
Yes.
Fabrication techniques. So, today, as a part of our series exploring the world of integrated circuits, we are going to look at how a chip is fabricated from the beginning to the very end. Fab engineering is a rapidly growing field that must go hand in hand with design engineering to bring a chip to life while meeting today's aggressive market requirements of higher performance, lower power, and smaller area. One very important thing to understand about fabrication is it is not ideal. Unlike simulations, the real world is full of variations, defects, and uncertainties. Devices don't always behave exactly as expected, and the processes rarely repeat perfectly. On the top of that, fabrication is performed at a massive industry scale where yield, cost, and economic balance matter just as much as physics. In many ways, fabrication is a real war. Engineers constantly fight against